Let's talk about multiplicative identities and inverses. So, what is a multiplicative identity? Let's take a look at an example where we know what's going on. Consider the real numbers r with usual multiplication. Then 1 is called a multiplicative identity because 1 times a is a times 1 is equal to a for all real numbers a. Similarly, for the integers, 1 is a multiplicative identity because 1 times a is a times 1 is a for all integers a. So whenever we have a set that's closed under multiplication, so there's a multiplication defined on it, if there's an element e that has the property that e times a is a times e equals a for all elements a in that set, then we call e a multiplicative identity. So we've just defined multiplication on matrices, on certain matrices, and so the question is there a multiplicative identity for matrices? The short answer is no, but for a silly reason. Right? So we can only multiply matrices together if the sizes are compatible in a certain way. Right? So suppose I have two matrices, A and B, an M by N matrix and a P by Q matrix. If I want A times B to be defined, then I need N to equal P. If I want B times A defined, I need M equals Q. If I want A times A defined, I need M equals N. And B times B to be defined, I need P equals Q. So if I put all those together and want to be able to multiply in these four different ways, then I need N equals M equals P equals Q to get a set of matrices where we can multiply all the elements together. What that means is we need a set of square matrices, right? Square and of the same size. And so the next question is there a multiplicative identity for n by n matrices? The answer is yes. So we'll let I sub n be the matrix, the n by n matrix. It's going to be diagonal, and along the main diagonal is all ones. Everywhere off the diagonal is all zeros. And this matrix In is going to satisfy In times A is A times In for all n by n matrices A. So for example, I1 is just this 1, I2 is 1, 0, 0, 1, I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. So oftentimes, we're going to just write the identity matrix as capital I if the size of the matrix is clear from the context. So now that we have an identity, a multiplicative identity, we can start talking about multiplicative inverses. And so again, we're going to go back to examples we understand and try to see how that generalizes. So for the real numbers, with usual multiplication, a multiplicative inverse of 5, for example, is 1/5. And the reason for that is 5 times 1/5 is 1/5 times 5 gives us 1, which remember is the multiplicative identity for this multiplication. So more generally, if I have a real number c, then the multiplicative inverse of c is 1 over c, since c times 1 over c is 1 over c times c is 1. Except that's a little bit of a lie. I need to also have that c is not 0. Right? If c is 0, then there is no multiplicative inverse for 0. Let's think about the integers. So again, with the integers, we had the multiplicative identity was 1. The multiplicative inverse of 5 is, well, it's not 1/5, right? Because 1/5 is not an integer. And so 5 in the integers does not have a multiplicative inverse. Only 1 and minus 1 are invertible in the integers. So in particular, in the real numbers, every non-zero element is invertible. In the integers, only 1 and minus 1 are invertible. So now, what's a multiplicative inverse? Well, a multiplicative inverse of an element A, if it exists, is an element C in that set that's we're talking about the multiplication on, that has the property that A times C equals C times A equals E, where E is the multiplicative identity. If A has an inverse, then A is called invertible, and the inverse is denoted with a superscript of -1. So now we're set up so that we can define inverses for n by n matrices. So an n by n matrix A is called invertible or non-singular if there's an n by n matrix, we'll call it A inverse, right? A superscript -1, that has the property that A times A inverse times A is the n by n identity matrix. The inverse, if it exists, it turns out it's unique. Okay, so let's look at an example. This matrix 1, 1, 0, 1, I claim that the inverse of that matrix is 1, -1, 0, 1. Now how would we check that? Well, all we have is a definition of what it means to be a multiplicative inverse, and so that's what we check. We just compute. The product 1, 1, 0, 1 times 1, -1, 0, 1, and I get the 2 by 2 identity matrix. And then I compute the product in the other order, and again I get the 2 by 2 identity matrix, which means the inverse is as it's stated here. In the next video, we're going to actually look to see how can we compute inverses when they exist.